Good morning everybody. Welcome to the next session, that is doubly reinforced beams. In the last session we have discussed the limit state analysis of singly reinforced beam. Now let us get into the doubly reinforced beam. So in this session let us learn what exactly is a doubly reinforced beam and what is the necessity of doubly reinforced beam and how exactly we are going to analyze the doubly reinforced beam and as per IS 456-2000. So let us discuss all these things in this particular class. Okay. So now first let me get into the definition. Okay, what is doubly reinforced beam? Okay, the doubly reinforced means if a RC structural element, that is beam, that is RC beam section having a steel reinforcement, RC beam section having a steel reinforcement both in tension zone and compression zone. Okay, that means the RC beam comprises of a steel reinforcement both in compression zone and tension zone is called as doubly reinforced beam. So you know the story, that is in the singly reinforced beam we used to provide the steel reinforcement in the tension zone, but in this particular case we are going to provide the steel reinforcement in the compression zone also. So that's what the doubly reinforced, the word, the meaning, the terminology. Doubly means both in the tension zone and in the compression zone. So in the both zones we are going to provide the steel reinforcement. So that particular beam is called as doubly reinforced beam. Okay. So you can see from the diagram, that is I am going to provide. So this was the case in the earlier, that is used to provide the reinforcement in the tension zone, that was a singly reinforced beam. So now in this particular doubly reinforced beam we are going to provide the compression steel in the compression zone also, So this particular thing is called as doubly reinforced beams. You can see the terminology is the same thing. Okay, these are all this yellow color one represents the area of tensile steel with the effective cover D dash, and this will be the width of the beam, overall depth of the beam, no change, and effective depth as we have defined, the effective depth is defined as it is the distance between the topmost, that is extreme compression fiber or edge of the beam to the centroidal axis of a tension steel is called as effective depth. It remains same. Now the new things we are going to see here is, that is a compression steel. I am going to denote it by ASC, that is compression steel, that is area of compression steel. Okay, so just like how exactly the area of tension steel will come, here also it will be area of compression steel. Is it clear? And also this area of compression steel will be situated at an effective cover D dash from the extreme compression edge. Okay, how exactly the D dash will be there for tension steel? Okay, the same thing we are going to deal with the compression steel also. That's why been written clearly, effective cover for compression steel, effective cover for tension steel. Is it clear? So this what exactly represents, or I can say, a doubly reinforced beams. Okay, if I am going to provide the reinforcement both in the tension zone and also in the compression zone, then that particular beams are called as doubly reinforced beams. Now immediately, okay, the question arises in your mind or in our mind. What is that question? Sir, why we are going to provide the compression steel? Why we are going to provide the compression steel on the topmost part or in the compression zone? Or what is the necessity of doubly reinforced beam? Why we require doubly reinforced beam? Is it clear? The doubly reinforced beams are required. Okay, that is necessary. The first one is, okay, or the first point I can say is, whenever you want to restrict the depth of a beam, okay, whenever you want to restrict the depth of the beam in which a singly reinforced doesn't have a capacity or inadequate to withstand that moment. Okay, for example, if I want to go for, or if I want to restrict the depth, for example, to a certain, a minimum depth or whatever the depth, okay, in that particular depth, okay, the moment of resistance will be more. That is, the mu will be more. In that particular instance, the AST, that is singly reinforced, is inadequate to resist those moment of resistance or moment. Okay, hence we are going to depend upon the doubly reinforced beam. So, by providing a doubly reinforced, or by going with a doubly reinforced, we can come across with a, okay, or we can resist a moment, okay, or we can go with a restriction in the depth of the beam. So, that is what the first point, or what is the necessity. Okay, whenever you want to restrict the depth of the beam, in that particular instance, the singly reinforced doesn't have a capacity to bear that moment, because when you are going to restrict the depth of the beam, the moment will be more. The singly reinforced is not strong enough to resist that moment, hence we are going to use a doubly reinforced beams, or I can say a compression steel and a tension steel. So, this is what the first point. Okay, and the next, whenever the beam is subjected to eccentric loading, that means a load does not pass through the central axis. If a load carrying capacity will be eccentric, so at that particular instance also we require doubly reinforced beams. Next, when you want to, okay, come across with something like excessive deflection, if you want to overcome the excessive deflection, so then we are going with the doubly reinforced beams. Okay, when you want to come across with a torsional effect in the beam, so then also we are going with this particular doubly reinforced beam. And also, okay, what I can say, change in the loading or reversible loadings. Okay, in that particular or alternative loadings I can say. When the beam subjected to alternative loadings also, at that particular instance, the singly reinforced beams are not strong enough to withstand all these things. Hence, I am going to depend upon the doubly reinforced beams or sections. So, this is what I can say a necessity, or why I require a doubly reinforced beams, because of these things. Is it clear? Is it clear? So, this is what a necessity. Okay. So, now we came to know what is the doubly reinforced beam and why we require doubly reinforced beam. Why we require doubly reinforced beam. So, now let us get into the analysis part. How the doubly reinforced beam, okay, will be analyzed. How the doubly reinforced beam will be analyzed. Okay. See, this doubly reinforced beam, okay, will be usually having a moment or ultimate moment of resistance greater than limiting moment of resistance. Please keep this in mind. Always, okay, in the doubly reinforced beam, the ultimate moment of resistance will be more than limiting moment of resistance, or I can say maximum moment of resistance. Okay, and therefore the doubly reinforced beam will be subjected to a factored moment. Therefore, doubly reinforced will be subjected to a factored moment which will be analyzed into sections. Okay, as I have defined in the diagram, let us see that how exactly it will behave. Okay, so with this, okay, the prerequisite, that is mu greater than mu lim. Okay, let us get in how exactly the behavior of analysis or doubly reinforced will see. Okay, see, this is what a beam, okay, of a width B and overall depth D, and we know the neutral axis will lie exactly at the center. Okay, next, and these are all the area of compression steel denoted by ASC, and these are all the area of compression steel. I have been defined with this AST has been defined with two colors. Okay, that is yellow and pink. Okay, I will make you understand what exactly is that one. Okay, so the 3 or 5 number of steels have been accommodated in the tension zone, that is what AST. Okay, so as I stated, because in the doubly reinforced beam subjected to a factored moment, okay, it will be analyzed into 2 sections. It will be analyzed into 2 sections. So that is, you can see the same beam, that is B, okay, and overall depth of a beam, that is D, okay, and this will be, okay, having a steel of 3 number, that is AST1. That means the section 1 will be analyzed same as singly reinforced. Okay, that means what I am trying to say here is, first section consists of moment of resistance. A first section consists of moment of resistance. Okay, or I can say a singly reinforced section having a moment of resistance mu1. Okay, that means what I am trying to say here is, I am going to analyze a section of this beam just like a singly reinforced. Just like a singly reinforced. So it will be having a moment of or ultimate moment of resistance mu1. mu1. Okay. So on which I am going to derive with the formula now. Okay. So please keep this in mind. Okay. In the first section, so this particular section will be analyzed same as a singly reinforced beam having a moment of resistance mu2. Next, come to the second part or a second section. Okay, in this particular section you can see, okay, in the compression zone I have been provided with the 3 numbers of, okay, compression bars or compression steel, which will be denoted by the area of, that is ASC, okay, with an effective cover D dash. Okay, next, this AST2 will also be provided. That AST2, why I am going to denote that as AST2? Because I am going to provide additional steel. Okay, I am going to provide additional steel. That additional steel will be called as AST2. AST2. So why this AST2 is provided? This additional steel is provided in the tension zone to balance the compression steel. The additional steel AST2 is provided to balance the compression steel. Okay, so that's why this AST2 has been provided. Okay, so remember this point, this AST2 or additional steel in the tension zone has been provided to take care or to balance the compression steel. So that is what the meaning of AST2. Okay, so in this particular thing, as I stated, in the section 1 it will be singly reinforced. So now it will be converted to doubly reinforced. That means it will be having a reinforcement in both the zones. And the next, it will be having a moment of resistance mu2. Okay, I am going to, okay, discretize the ultimate moment of resistance into 2 sections. One is mu1, that is singly reinforced, and mu2, it has been doubly reinforced. Is it clear? Okay, so this is the regarding a doubly reinforced section behavior. Is it clear? Next, coming to this stress block or stress strain diagram. Okay, now I am going to consider the same beam, that is the width of a beam is B and overall depth of a beam is D, with the same area of compression steel, with the same area of tension steel. Okay, and it will be denoted by, okay, effective cover D dash and effective cover D dash at the bottommost zone or tensile zone. And the next, the effective depth D. Okay, and this particular thing, okay, the variations will be what I can say. If this is overall depth, overall depth minus effective cover will give you this d minus d dash distance. So this d minus d dash distance is the distance between the centroidal axis of a compression steel to the centroidal axis of a tension steel. So that particular distance is d minus d dash. So based upon the d minus d dash, the variations will change. The stress strain diagram will change. So let us see how exactly it will change. So now, this is what the stress diagram, or can see the parameters. Okay. This particular will be the ultimate compression in concrete, ultimate compressive strain in the concrete. Okay, ultimate compressive strain in the concrete denoted by epsilon Cu, which is equal to, or exactly like what I can say, maximum compressive strain in the concrete, which will be equal to 0.0035. Okay, maximum compressive strain in the concrete, which is equal to 0.0035. Okay, and coming to the bottommost zone, that is tension zone, that is will 0.87 Fy by Es plus 0.002. So this will be the, okay, the strain in the steel. This will be the strain in the steel, which will be given by 0.87 Fy by Es plus 0.002. Now coming to the variation of this stress strain diagram, you can see this particular in the distance between the extreme compression fiber to the centroidal axis of a compression steel, it will be something like a rectangular variation. It will be a rectangular variation. Okay, and it will be subjected to a compression force because it will be split into two variations, and so I am going to, okay, one is rectangular variation, another one is parabolic variation, as you have been learnt in the stress block parameters. Okay, so this particular rectangular variation, okay, that will be C2. C2, that is a compressive force C2 is equal to FSC. Okay, that is stress corresponding to the compression steel multiplied by the area of a compression steel. That is what C2. Okay, and next in another variation, that is coming to the parabolic variation. So this is what a parabolic variation. In this parabolic variation, okay, C1 will be acting. So it will be given by 0.36 FCK into B into XU. So this will be your C1. Okay, and this distance from extreme edge compression fiber to the C1, okay, will be a 0.42 XU. 0.42 XU. So that will be the, what I can say, a distance. Okay, that will be acting, okay, by a C1, that is compression force 1. And from C1 to the centroidal axis of a tensile steel will be D minus, that is effective depth D minus 0.42 XU. So the remaining distance will be D minus 0.42 XU. And XU, you know that is the neutral axis depth of a rectangular doubly reinforced beam. Is it clear? And this is the tensile force T, which will be acting away, which is given by, or which will be given by 0.87 Fy into AST. So this is what a stress strain diagram. So now if I am going to come across with a formula, so that is mu1 corresponding to the first section. mu1 corresponding to the first section will be C1 into lever arm. C1 into lever arm. Okay, this is regard to the first section. Okay, so that is, it will be singly reinforced section, that is C1 into lever arm. So that is C1, which will be given in the stress block parameter or in stress strain diagram, that is 0.36 FCK into B into XU. And then the lever arm distance or the perpendicular distance of that C1 about the centroidal axis of a steel is D minus 0.42 XU. So this will be your mu1. Okay, and the same way Next come to the mu2. Mu2 means that is the moment of resistance corresponding to the section 2, which will be a doubly reinforced section. That is C2 into lever arm. C2 into lever arm. So C2 which will be given by FSC. Okay, FSC means the stress corresponding to the compressive steel. Okay, into ASC, that is area of compression steel, multiply by the lever arm distance of that C2 about the centroidal axis of a tension steel. Because so this is the what I can say the moment center point in which I am going to consider a C1 and C2. Okay, the C1 is C1 into that is into lever arm distance, that is d minus 0.42 XU, and coming to the C2, that is C2 into d minus d dash. Okay, so this will be your M2. Okay, next, therefore Mu, okay, the total ultimate moment of resistance Mu equal to Mu1 plus Mu2, Mu1 plus Mu2, which will be 0.36 FCK B into XU into D minus 0.42 XU, okay, plus FSC into ASC into D minus D dash. So this is the formula you are going to use in the ultimate or to calculate ultimate moment of resistance for a doubly reinforced section. Okay, and coming to this, okay, the IS456, okay, coming to the IS456. So in the singly reinforced section, okay, we have been defined, that is Annex G, page number 96. We have been discussed class G 1.1. So class G1 is for rectangular section. Okay, till now we have analyzed only for rectangular beams or rectangular cross section beams. Okay, G 1.1 which we have been derived till last session will be for singly reinforced section. Now we will come across G 1.2, that is for doubly reinforced sections. So in the IS456 they have been clearly defined G 1.1 section without compression reinforcement, that means for a singly reinforced section. G 1.2 section with compression reinforcement, it is clearly indicating it is for doubly reinforced. So in IS456 they have been given a one more formula or alternative formula we can also use as per Annex. Okay, G 1.2 as per Annex G 1.2 to calculate the ultimate moment of resistance. Okay, that is Mu minus Mu lim, okay, which is equal to FSC into ASC multiplied by D minus D dash. This is the one more formula we are going to use to calculate the ultimate moment of resistance, okay, of IS 456 2000. Okay, so this is the one more formula we are going to use as per Annex G 1.2 page 96. Okay, that is if you want Mu, okay, that is Mu is equal to Mu lim plus FSC into ASC multiply by D minus D dash. You can use either of the formula to calculate the ultimate moment of resistance for a doubly reinforced sections. Is it clear? Okay. So next FSC as I have stated, let us see. You know how to calculate Mu lim. You already know how to calculate Mu lim. Okay, in the singly reinforced we have been derived. Mu lim can be calculated. Okay, that is based upon the grade of a steel. Okay, that is 0.138 FCK BD square, 0.133 FCK BD square. Okay, all those formula, okay, are the same formula will be applied here also. Or you can use G 1.2 C formula to calculate a Mu lim. So that won't change. The mu lim means limiting moment of resistance. Coming to the FSC. So this is the new terminology, FSC. So this is the design stress in compression steel corresponding to the, it is a very important word, corresponding to the strain in compression steel, which will be epsilon Cu equal to 0.0035 into Xu max minus D dash divided by Xu max. That means what I am trying to explain here is we are going to calculate the design stress in compression steel based upon epsilon Cu value. If you want to know the FSC value, first you should know the epsilon Cu value. By knowing the epsilon Cu value, you can calculate the FSC. Okay, so that will be calculated based upon the new code, that is SP16, design aids for reinforced concrete, or you can use IS 456, which I am going to teach you when I am going to solve the problem. Okay, and the next Xu max you already know, and the next D you already know, that is effective depth. Okay, this terminology is also known. So next, a very important terminology, D dash. D dash means effective cover for compression steel. You need to be very careful. In the problem they are going to mention effective cover for compression steel, effective cover for tension steel. In a hurry, if you are going to substitute effective cover for tension steel, the whole problem goes wrong or analysis goes wrong. So you need to be very careful. This D dash implies the effective cover for a compression steel. Since I have been analyzing for doubly reinforced section, you need to consider D dash as the effective cover for this. Next, coming to the total area of a steel, that is AST. Okay, if you want to calculate the AST, okay, in the doubly reinforced, which comprises of AST1 plus AST2. AST1 plus AST2. So you already know AST1 means that is the area of a tensile reinforcement corresponding to the singly reinforced section. AST1 corresponding to the area of the steel for a singly reinforced section. That means I am going to calculate AST1 just like or same as singly reinforced section, which I am going to teach you while doing analysis. Okay. Next, AST2. So this is what I have been told, that is area of a tensile reinforcement or additional steel that will be required to balance the compression steel. That is what AST2. That means additionally we are increasing the number of a bar in the tension zone to take care of a compression zone or compression steel. Okay, so that is also given in the code book, that is AST2 is equal to ASC into FSC divided by 0.87 Fy. Okay, ASC into FSC divided by 0.87 Fy. So this is the formula. So like this we need to keep on calculate all the parameters, mu lim, FSC, ASC, okay, D dash, okay, then AST. So after calculating everything, then if you are going to substitute in the main formula, then you are going to come across with the ultimate moment of resistance for a doubly reinforced section. Okay, for a doubly reinforced section. Okay, and a very important thing we need to note here, we need to note here. Okay, once again I am going to stress in the analysis, that is this formula holds good for under reinforced section. If you are going to use this particular formula, this formula holds good for under reinforced section. If a section, if you are going to come across with a over reinforced or a balanced, then you will need to replace this Xu by Xu max. you need to replace a formula, that is XU by XU max. Then the formula will be 0.36 FCKB into XU max multiplied by D minus 0.4 to XU max plus FSC into ASC into D minus D dash. This is a very, very important note you need to remember. This formula holds good for underinforced section. If you are going to come across with a overinforced section, okay, or a balanced section, then this XU need to be replaced by XU max. Okay, so once again I am going to discuss or stress while doing a problem also. Okay, so this is regarding a doubly reinforced section. So today we have been discussed or defined what is the doubly reinforced beam, why we require doubly reinforced beam, okay, and how exactly it will be analyzed, okay, dividing into sections. Okay, next is stress block parameter or stress strain diagram and its ultimate moment of resistance. And next, how to calculate as per the code. So these are all the things we have been discussed in this particular session. We will continue with the analysis or a problem of doubly reinforced rectangular section in the next class. Thank you.